Hello, Chemistry 1110 students. We're going to begin here with Chapter 6, and here we are going to learn about how to represent molecules and understand how they are put together. The first thing you need to be aware of is the octet rule, and I know we've talked about this before. Everything wants to be like a noble gas, and so atoms will lose, gain, or share electrons in order to attain that noble gas configuration. So I have an example of how fluoride gas is formed. You have two fluoride atoms, each with 7 valence electrons, and by sharing those single valence electrons, they each can feel like they have a full octet. Note that only valence electrons contribute to bonding, and so in this case I said fluorine has 7 valence electrons. It's 2s2 and 2p5. All right, since only 2 of those valence electrons participate in the formation of the F2 bond, we can show it as different colored dots, or quite often when it's a bond we show it as a dash between the 2 nuclei, and the valence electrons that are not involved in bonding but they're still sitting there are called lone pairs. So Lewis structures, and this is the same Lewis that came up with the electron dots, is a way to represent covalent bonding so we can understand how molecules are formed. And so these are shared electrons that we're interested in, and they're shown as either pairs of dots or dashes, as I discussed before. And the same with the lone pairs, they are generally shown as pairs of dots. So I've got 2 examples here. They're both H2O or water. Hydrogen only has 1 valence electron, and it shares it with the oxygen, so hydrogen thinks it has a full isoelectronic configuration like helium. Oxygen sees 8, or you can write it as is shown on the right. All right, there's some things we need to know. In a single bond, atoms are held together by 1 pair of electrons, but you can have multiple bonds where, for instance, in a double bond, you have 2 pairs of electrons being shared. And so here we have water again, just showing a single pair of electrons that result in a bond. And next to that, I'm showing you CO2. And in order for both of the oxygens and the carbon to see 8 electrons, we have to put 2 pairs of electrons between the carbon and the oxygens, and that is a double bond. Now, if we looked at a triple bond where you can have 3 pairs of electrons, example is nitrogen. Nitrogen only has 5 valence electrons, so for 2 nitrogens to form N2, they have to line up like this. They each have a lone pair of electrons and they share 3 pairs of electrons. All right, something about multiple bonds is that we need to look at bond distance, which is that distance between the 2 nuclei of the covalently bonded atoms. Remember, covalently means the electrons are shared. And multiple bonds are shorter than single bonds. And I've always thought of this as wrapping in a rubber band numerous times. If you wrap it twice around something, it's going to be tighter, and the 2 items are going to be held closer together than if you just put the rubber band on in a single stretch. So I have examples. CO has a triple bond, and N2 has a triple bond, and they're very short. When you compare them in this table, we have a significant number that you can compare. For instance, the CN is 143, that's picometers. CN, where it's a double bond, is 138, and C triple bond N is 116. So we see that they get shorter with the larger number of pairs of electrons holding them together. The other thing is that multiple bonds are shorter than single bonds, and triple bonds are shorter than double bonds, where double bonds are shorter than single bonds. So I have an example here with nitrogen-nitrogen bonds. The other thing is that those shorter multiple bonds are stronger than a single bond. Once again, that analogy of wrapping a rubber band multiple times pretty well holds with this. And we can quantify that bond strength by measuring the quantity of energy that's required to break it. And we'll look at this more in Chapter 10.